So welcome everyone to our CPPC seminar in front of a live studio audience. We have Michael Baker from the University of Melbourne. So Michael is from the UK. He got his PhD from the University of Oxford before moving to positions in Valencia, Mainz and Zurich, before starting a position as a research fellow at Melbourne. So Michael's worked on various particle theory, particle phenomenology stuff in the past, dark matter stuff in the early universe. And today's going to be talking to us about particle physics and some very, very timely topics. So thank you for being with us, Michael, and take it away.
Okay, thank you very much. Thank you for the invitation. It's great to give a talk to you guys, and nice to have some live audience. I think this is a bit of a luxury in seminars these days. Right, yeah, so today I'm going to talk about radiative fermion masses, related Higgs measurements, and a connection to g-2. And this is based on two recent papers, one which has recently been published in JHEP, and the other one which is under review with Peter Cox and Raymond Volkers, both here in Melbourne. Okay, so I'll start with a bit of an extended motivation. So as we know very well in the standard model, there's no simple fermion mass terms because the left-handed fermions are SU2 doublets, the right-handed are singlets. You can't just write down a simple fermion mass term. You have to write down something like this term on the left, or in the standard model, you write down exactly this with the Higgs doublet making it an SU2 singlet. Then after electroweak symmetry breaking, you get two contributions from the Higgs doublet, one the physical Higgs boson H, and then you get the VEV V. So we see that this term of the VEV leads to a fermion mass term, and then the mass is given by Yakawa coupling times the VEV over √2. But we also see with the physical Higgs boson also being produced, and importantly with the same coupling, then yeah, the final, for instance, of the physical Higgs boson coupling to the fermions is this minus I y over √2, which is exactly proportional to the mass. So there's two important points I want to make here. One is that the coupling of the Higgs boson to the fermions is related to the fermion mass in this precise way. And secondly, on the left-hand side, the fermion masses are given by a Yakawa coupling times the Higgs VEV. Now, if we look at the masses of the fermions in the standard model, so we've got the masses on the x-axis here, and then it's just the generation number on the y-axis. On this plot, the up type and down type have just been offset from the horizontal line just a little bit. I think it's just so you can see the S and the mu. But anyway, the main thing is the masses of the different particles. I should say in this talk, we're not going to deal with the neutrinos at all. That's a whole other complicated topic as to how to generate neutrino masses. We're going to focus only on the charged fermions. So we see the VEV of the standard model. The VEV of the standard model is around 200 GeV, which is near the top quark. So the Yakawa for the top quark in the standard model is around 1. And we see that all of the other charged fermions have much lighter masses. So this means that Yakawa couplings are quite small. So while this is technically natural, this hierarchy we see in the fermion masses is weird and sort of requires some, or we expect it to have some deeper explanation. So as I've said, the top quark has a coupling around 1. It has a mass of the order of the electroweak VEV. And then I kind of want to draw your eye to this group of particles in the middle from the S and the mu up to the B. These are all sort of grouped together roughly a bit lower than the VEV. In fact, so if we look at those particles, the masses are roughly equal to VEV over 16 pi squared. And while this may be just a numerical coincidence, it is possibly suggestive of how these, or why these masses might be as low as they are. So in the standard model, we saw we had this tree level coupling between the Higgs and the standard model fermions. And this 16 pi squared is suggestive of replacing the tree level coupling with a one loop coupling, a one loop effective vertex. And so this is an old idea. Many, many models use it. I'm not going to list all of the references. There's far, far too many. But one point of difference to sort of how this has been viewed in the past to our motivation here is that many of these, many of the older models, they're typically aiming at a complete UV model of flavor. So to explain all of the fermion masses, perhaps explain the CKN matrix, perhaps neutrinos, perhaps PM&S, and have a complete model of flavor. We're going to be much less ambitious in what we're doing today, and I'll tell you precisely what that is a little bit later. The important point I want to make for now is with these a one-loop generated coupling between the Higgs and the fermions. After electroweak symmetry breaking, we have the Higgs doublet here. As before, you get the physical Higgs and the VEV, and this produces, the VEV produces a mass term, so the diagram on the left, and the physical Higgs produces the effective coupling of the Higgs to the fermions. Now, the important point in these one-loop radiative models, this sort of tree-level relation between the mass and the VEV is, in general, it doesn't hold anymore. So an interesting point is that in these one-loop radiative models, you get a violation of this relation between the mass and the coupling of the physical Higgs boson to the fermions. And it seems that this fact is possibly underappreciated. And in searching the literature, we only saw this kind of highlighted in a handful of papers. Maybe part of the reason for this is, in the 80s and 90s, when these ideas were really being developed, no one knew that the Higgs existed, and its couplings to the fermions certainly couldn't be measured. And the situation is different today. So I'll just give you a quick review of the experimental situation. So in 2012, the Higgs boson was discovered. And at that point, all you could really say about the coupling of the Higgs to the charged fermions is that the top Yakawa was roughly equal to 1. So even though that the Higgs was originally seen in the diphoton channel, its main production mode at the LHC is gluon-gluon fusion, which proceeds, it's dominated by a loop of tops. And so the main production channel of the Higgs boson at the LHC, it's the Higgs coupling to the top via a loop. And because the production cross-section of the Higgs boson was roughly as expected in the standard model, we knew that the top Yakawa sort of had to be 1. Well, that was the first kind of measurement. But that's not very much information to go on if you want to be trying to constrain models of radiative mass generation. So almost to 2016, here we have a plot of the particle mass on the x-axis and its coupling to the physical Higgs on the y-axis. And so the dotted black line that goes diagonally, this would be the standard model expectation. And you see that all of the charged fermions lie nicely on this. The top has its coupling of around 1. The B and the tau were measured. And in 2016, there was just an upper limit on the possible coupling to mu's. It extends down to all the way down to 0. In 2020, by this point, quite a lot more data had been collected, and the measurements had improved quite significantly. So we see on the bottom here, we've got the ratio to the standard model, and the mu, the tau, the B, and the top are all measured to sort of better than 30% accuracy. So this has been a huge improvement in our understanding of the coupling of the Higgs to the charged fermions in the last 10 years. Looking to the future, at the end of high Lumi LHC, which will be around 2040, you see that the error bars, this is a projection from CMS with 3 inverse autobahns, the error bars have shrunk and they're almost invisible here. We can see what they actually are in the next plot. So if we go to the even further future, post LHC, we're now sort of considering what the next collider might be, and these sort of decisions are being made at the moment. Here I've got some projections for the Fcc program, and now because the errors are so small, we've changed what we're plotting, and now it's in fact the relative error in the measurement for each of these couplings. And so in green is the high Lumi LHC plus LEP, And you see there is expected the mu, the tau, the top, and the b to be better than 10% accuracy. So yeah, from the 30% today, by the end of high linear LHC, it's going to be better than 10%. And then following a program like FCC, it's going to be better than 1% in all of these, for all of these couplings. So as I say, the experimental situation has changed dramatically in the last 10 years. And we're now at a very important time where we're considering which future collider programs may be the most promising, what's feasible, what's cost effective. And so now is perhaps an ideal time to revisit the radiative fermion mass generation scenarios. So like I said, many of the older papers before the coupling of the Higgs to the fermions had been measured, these were kind of aiming at UV models that could explain the whole flavor structure. We're going to be much more limited in our ambitions, and we're going to kind of start from this just the one loop diagram that's necessary for producing the effective mass, and we're going to look at all of the sort of observables or the deviations from the standard model that necessarily follow from the fields and couplings that appear in that diagram. So like I've already said, the coupling of the Higgs to the fermions, this gets a deviation from the standard model expectation. Also, from the Higgs doublet, we know the Goldstone bosons are eaten by the gauge bosons. And so this is going to lead to a deviation in the Z couplings to the fermions as well. You get an extra contribution there. And this necessarily follows from the mass generation diagram. Another aspect is because the Higgs has hypercharge, at least one of the particles it couples to has to be electrically charged. And this means you get contributions to Higgs gamma gamma via a loop of that charged particle. So this is something you also can't avoid. This next one is the analogous to gluons. This is perhaps avoidable, it depends on the model, but if any of the exotics have color charge, any of the particles, when I say exotics, I mean the 3 new particles we're introducing in that loop. If any of those particles have color charge, then you're going to get a contribution to Higgs blue loop. Right, then from this, the second process, from the Z loop, we could see that instead of coupling to fermions, we could close this loop and we get sort of this kind of diagram and potentially similar for the W and the photons. And so then we get contributions to the electroweak oblique observables, the STU parameters. And these are very well measured. I mean, this is another thing that you definitely have to check. These could, in fact, give you better sensitivity than some of the Higgs observables. Another observation, if we take sort of the Higgs coupling to these 2 fields, we can close that loop. And then we get, assuming these exotics are heavy, when we integrate those out, we get a threshold correction to the Higgs mass parameter in the standard model. And if that's too large, then you can generate a fine-tuning problem. So there's naturalness constraints that you may want to consider. This kind of sits a little bit differently to the others, where the others are really experimental or related to experimental observables. The naturalness is more of a theory consideration, but it's definitely something that you want to take into account and understand. And then finally, because the fermions, they couple to at least one of these 2 particles has to be charged, then this leads to you can basically attach a photon line to the mass diagram that we had. And then this is going to give you a contribution to G-2. Okay, so this is kind of, the motivation that we have is that now is a very interesting time to look at these Higgs to charge fermion couplings. It's being measured experimentally. And if we just want to generate one mass radiatively, then what are all the necessary consequences that have to follow from that? There are, of course, other consequences. I'll briefly mention this at the end. So, I mean, if these exotics are color charged, then you can get large direct production and colliders. But then exactly what the limits will be from that depend on their decay channels and so on. And we really want to focus on just what are the necessary observables that are tightly connected to the radiative mass generation. So we won't have much to say about this. They're very model dependent. So that's kind of our setup. I just wanted to give you a slide on exactly what we've done and kind of what's new compared to what exists in the literature. So the first thing that we did was a systematic classification of models. Oftentimes in the literature, people look at one particular model with some given charges, and we thought there was some benefit to understanding the range of possible models that are out there. Then for that set of models in general, we calculated the effective masses and the Yakawa couplings that you get. And then, like I just talked about, there's all of these necessary consequences. So we calculated these additional deviations, and many of these we did for the first time. We then performed some phenomenology of the benchmark models to understand whether these LHC experiments, the measurements that have recently done, whether they exclude the radiative models or not, or what's going to happen in the future. We didn't really have a good understanding of this before we started. So we wanted to perform some phenomenology of some benchmark models, both with the existing constraints and looking forward to the future as to what to expect. Okay, so that was the motivation. Now I'll just give you a brief outline of the rest of the talk. So I'll first introduce some assumptions. So for any model classification, you have to make some assumptions. And we see very quickly that from our assumptions that you have two classes of model, which we call very imaginatively class 1 and class 2. So within class 1, I'll first talk about the classification of that set of models, talk about the radiative mass generation calculation, and then go into the phenomenology of a minimal model. Yeah, maybe I'll mention just here, well, most of the time we're interested in doing just one fermion at a time, so either the B or the tau or the mu. From our systematic classification, we realized that there's a class of models where you can do both the B and the tau without introducing any extra new fields or new couplings. So those to us looked particularly appealing. And so I'm going to talk about that, the phenomenology of that particular model. And then after that, I'll sort of show you the similar steps for the class 2, do the classification there, talk about the radiative mass generation. And in that case, I'll talk about the phenomenology of a benchmark muon model. Okay, so before we get into all of that, maybe now's the time to ask if there's any questions on the motivation or the setup. Okay, great, all clear, so let's go on. So like I said, to perform any model classification type program, you have to make some assumptions. You need to limit yourselves somewhere. And the assumptions that we made for our model classification, first, the tree level mass has to be forbidden, and we say it's forbidden by some symmetry. Secondly, that we generate the one loop radiative mass. So in our philosophy, we're really considering either the B or the tau or the mu. And once we've done that for the model classification, we'll make this observation that we can do both the B and the tau at the same time. But at the level of the model classification, we're really considering just one of these particles at a time, the B or the tau or the mu. We want to introduce only the necessary fields and couplings. So we don't have him. I mean, we expect that our model is going to be a part of a larger UV model to explain all of the flavor problem. But we really wanted to limit ourselves only to the necessary fields and couplings that you really need to generate that radiative mass. So while our analysis will be able to tell you something about larger models that have our submodel embedded in it, we're interested really in studying that submodel and the necessary fields and couplings. And then, so what kind of fields are we going to introduce? The exotic fields we introduce are either going to be scalars that do not obtain a VEV, or they're going to be vector-like fermions, so we don't have any problems with anomaly cancellation. We're also not going to introduce any extended gauge structures, so there's going to be no new vectors and no new gauge symmetries in the models we discuss. So there's some of these assumptions may be relaxable, and then you can do a larger model classification, but we thought this was a very reasonable place to start. So with these assumptions, you start to try to write down radiative mass diagrams, and you very quickly realize there's only two possible topologies. Either one with two scalars which couple to the Higgs, and then a fermion line along the bottom, which we call class 1, or the case where two fermions couple to the Higgs, and then with a scalar line along the bottom, which we call class 2. So as I said, for the first part of the talk, I'm going to talk about class 1, and then towards the end, switch to class 2. But for now, we're just going to talk about this class 1 diagram, where we have two scalars and one new fermion. Here I've written the fermions as, this L can be either the mu or the tau, and then we have the B. This is what we've done all of this. First of all, I'm going to talk just about the lepton. So the first bit I say here will apply to the tau and the mu models. So we just have the leptons. So these are the possible fields that can be there. We can then write down the Lagrangian terms that are necessary. So we have this first coupling is this vertex here. The second coupling is this vertex, two fermions in the scalar. And then up here with the Higgs, it's a dimension 3 operator. And so the coupling here has a mass dimension 1. We give it the name A. And so we have this trilinear coupling. Also, you'll notice to generate the mass, then you need necessarily to have a chirality flip. So we have a right-handed lepton here and a left-handed lepton here. And so that means in this psi propagator, there needs to be a mass insertion somewhere. You get in these one-loop models, you get the chirality flip from a chirality flip of the psi. So this is why we've written down the mass term. Okay, so this is the fields and the Lagrangian that we're interested in. Now to determine the allowed quantum numbers of the fields, we're going to look at the symmetries. So first, the U1 symmetries. So first there's the local U1 symmetry of hypercharge. And so all of these external fields have some hypercharge. So for this to be conserved at each vertex, then the difference between the exotics is fixed by the hypercharge of the external field. And so that means that there's some unconstrained hypercharge that you can add to all of these fields at once. And it's just the difference between the hypercharges of these fields that's fixed by the local U1 symmetry, by that local U1. There's also a lepton number. These external fermions have lepton number. And so the lepton number can either be carried by the psi or by the two scalars. It doesn't matter, but they have that. We see that there's also an exotic particle number. So all of these vertices, there's two exotic particles. So there's a global U1x respected by transforming these fields. So there's these three U1 symmetries, but we'll notice that none of these do the job of forbidding the tree-level Yakawa, which we insist on. However, there are two softly broken symmetries which are going to do that job. So one of the softly broken symmetries we call it SA, and you can see this symmetry if you set A to 0. So this coupling between the Higgs, the E2, and the phi vanishes. You then see that you can charge LR and eta under some U1, and then it's only softly broken at this vertex by this trilinear coupling. And now the point is that as long as the symmetry is only broken softly, then the tree level Yakawa is forbidden, because the tree level Yakawa breaks, it's a hard breaking of this symmetry. By which I mean here, this is a dimension 3 operator, so its coupling has scale. Here is a dimension 4 operator, and the coupling has no scale. So the fact that the Yakawa term is forbidden means that it can't act as a counter term. And so this tells us that the effective Yakawa coupling that we generate from this diagram can't be divergent. Yeah, so this is the importance of having soft breaking of the symmetry that forbids your tree level. That's one of the two softly broken symmetries. The other one we call S psi. And so you can see this if you set the mass of the psi to 0, then you can charge L right and psi left under a U1, and then it's just broken at a mass insertion of the psi. And again, this is a dimension 3 term, and the coupling is dimension 1, so it's a soft breaking of the symmetry. Okay, so that's all for the U1 symmetries. There's also the non-abelian symmetries. And so in this, for the lepton models, the external states are all uncolored, so it means all the exotics have to be in the same SU3 representation. Here for the SU3 representation, we're using Dynkin indices. So 0, 0 would be the trivial one, 0 is the fundamental, 0, 1, anti-fundamental, 1, 1 is the octet. But here, because none of the states have SU3 color, all of the exotics have the same representation under SU3. Under SU2, the Higgs and the left-handed lepton both have SU2 charge, and so this means that phi has to differ from eta and psi by 1. Okay, so we can summarize all of this in some large table where we have the 4 exotics that we're introducing. We've split the psi into its chiral components, into vial spinners. We see the hypercharge Y, and there's this unconstrained Y psi that we talked about. Only the differences between these are fixed. And then we've got lepton number, the global U1x, the exotic particle number. We've then got our softly broken symmetries. And here we've written the models that only have trivial or fundamental representations of the non-abelian groups. And we see that there's 6 models here that we might want to consider. So in the paper, when we look at the benchmark models, we pick one that has the smallest number of fields, for instance. Okay, so that's the complete model classification for the tau and mu models. I'll just quickly tell you about the B models. So here you see the external states have changed to the quarks. We have a slightly changed Lagrangian. And the main difference, of course, now is that the B and the Q have color. So there's a slightly richer a set of possibilities for the SU3 representations of the exotics, and that's given by these 3 choices here. But when we go and do the same job and look at the minimal models, it turns out there's still just 6 minimal models, even with that richer structure. Yeah, that's what I want to say there. But so one of the benefits of doing a kind of model for classification like this is that you can find particular cases or relations that you might not have been aware of by thinking of individual models. And one particularly interesting one that we found is that with the same 3 particles, there's certain choices of quantum numbers that allow us to identify the set to generate, say, the tau mass, and the set that generates the B mass. And that's if you do this identification in the box here. And so when you look at that, it turns out that this unconstrained hypercharge that we had for the exotics, this disappears, this becomes fixed. So there's now only one choice of the hypercharge for which you can make this identification. The U1x that we had gets broken down to a Z2, we see that we have now both a U1 lepton number and baryon number. And we see that there's, for the trivial and fundamental representations, there's two possible choices of the gauge quantum numbers here. So when we talk about the phenomenology, I'm going to talk about this one of these two models for two reasons. One is that if you're sort of motivated to look at radiative mass generation, you sort of have in the back of your mind that you want some kind of more minimal explanation than the standard model explanation. So this is an appealing way to go in terms of minimality. And then also the constraints that you get from the B and the tau side basically just superimpose on top of each other. So it's kind of a way of being able to talk about the relevant tau and B models just at the same time and show the constraints on the same plot. So it's efficient in that way as well. But before we get on to the phenomenology, I just want to say a few words about the radiative mass generation in these class 1 models. So our starting point is this diagram. And so then what happens on electroweak symmetry breaking? We have this trilinear vertex here, which is the A Higgs eta phi. On electroweak symmetry breaking, one of the contributions, the Higgs gets replaced by the VEV. And now we see this leads to mixing between the E2 and the phi. So then you have to go to the mass eigenstates. So then we have some mixing between E2 and phi, which we call phi tilde and eta tilde, and with some mixing angle that's given by this, where M1 is the lighter of the mixed scalars and M2 is the heavier of the mixed scalars. So when we plot, we're going to plot things as a function of M1 and M2. So I'm kind of partly showing this to show the mixing, but then also just to introduce the notation of the lighter mass eigenstate is M1, the heavier one is M2. And yeah, this is a mixing angle. So I think it's instructive to just briefly show the expressions that we get for the mass and the effective Yakawa. So this first diagram, this is what generates the mass in these models. When you calculate that, the mass turns out to be, you get the 1/16 pi squared as we expected from the beginning. Then we have a product of the couplings that were at the vertex in the original diagram. We then have some product of masses and the trilinear coupling. This N2 here is this is a group theory factor that comes from the SU2 representations that just counts the number of particles going around in this loop. And similarly, D3 is an SU3 group factor that counts the same thing. And then F is just some loop function, which depends on the ratio of these exotic masses. Yeah, maybe something to say here as well is the soft breaking parameters are this A and this M psi. So you would expect the mass to end up being proportional to the soft breaking parameters, which you can explicitly see here. Now, when we go on to the effective Yakawa coupling, this is, when you just calculate it, of course, you get the product of couplings and so on, but then using this term above, you can rewrite those in terms of the mass of the fermion. And the suggestive reason for doing this is we see that in the limit that theta goes to 0, then this term becomes 0, this term becomes 1. We recover the tree level relation that you have in the standard model, but only in the limit of 0 mixing. And so kind of this is what I mean when I say that it's typically violated. But you can see that as you go to smaller mixing angles, you're going to get less of a deviation from the standard model expectation. And we can see that explicitly here. Now we calculated a bunch of other loops. I'm not going to take you through all of that. I think it's more interesting to just go on to the phenomenology. So the benchmark model that we going to consider, I said for the combined B and tau model, there were two choices of the non-abelian gauge quantum numbers. And this particular choice has the fewest degrees of freedom. So we call it the minimal model, and we're going to study this one. Okay, so here's we choose a particular parameter slice. We're plotting as a function of the lightest mixed scalar mass and the trilinear coupling A. we fixed the two Lagrangian mass parameters of the scalars equal, and now this corresponds to maximum mixing. And then you have, it turns out you have this relation between the two scalar mass eigenstates. We also have the mass of psi is yet to be fixed. We're going to fix it to be M2 here, but the results are really weakly dependent on exactly what M psi is, as long as it's the same scale as the other masses. That's the main thing. Now in gray here, we have some theoretical constraints on our parameter space. So we know perturbative unitarity has to be satisfied. These Yakawas have to be less than more or less root 4 pi. So this, in this bottom right region, this is where the Yakawas are coupling these fields to the B when they're both larger than, or when the product is larger than root 4 pi, then you'd be in this region. We then see some contours where the product is equal to 4, 2, and 1. So if you really don't want to, I mean, as you go to larger Yakawas, you're going to start to worry about Landau poles and things like that. So you feel safest when the Yakawas are sort of equal to 1 or not much bigger than 1. And then it's sort of a matter of your taste about how close to the this perturbative unitarity bound you're willing to go. So that's for the Yakawa couplings. We also have a trilinear coupling, which also has a perturbative unitarity bound. This is a little bit more complicated to calculate. You have to look at all of the 2-to-2 processes that involve the trilinear coupling, and then you do some diagonalization, and then you look at it as a function of the square root s of the process. You find anyway, it's a relatively involved computation, and we use the Serres-Fino framework to calculate that. They've recently implemented this originally for not colored, and then very recently also for colored particles. So we use the Serres-Fino framework to calculate this perturbative unitarity bound. But so we see, kind of as expected, to generate the B mass, you can have order 1 Yakawas. But one interesting thing to note here is that there's a kind of non-decoupling that's going on. So you may expect, just looking at the loop, that as you make the scale of new physics heavy, so M1 is say 10 to the 5, A is 10 to the 5, you're trying to just decouple the new physics. You may expect that you can no longer generate the effective mass. And it turns out that you can. There's sort of like this non-decoupling direction. So for trying to exclude these models or put constraints on these models, this looks like a nightmare because you'd never be able to just exclude an arbitrarily heavy particle. But then something we realized is that if you do make this new physics mass scale arbitrarily heavy, then you're going to generate a fine-tuning problem, like I said before, just from this diagram, from the standard model Higgs. And again, it's a bit of a matter of taste about exactly what level of fine-tuning you're willing to take on. And so using a particular measure, we've plotted where you have more than 1% in 1 per mil fine-tuning. So it's a bit of a matter of taste about how far into this gray region you're willing to go. But it does have the benefit of like having a cutoff on the mass scale. Then, okay, onto some of the Higgs observables, which was part of our main motivation to looking at this. How much do these Higgs observables constrain these radiative models? And so it's not just the coupling to the, here it's the B's, it's not just the coupling to the B's that's measured at the LHC, it's the signal strength to B, which is a product of production cross-section and branching ratio, and the Higgs width comes into it as well. So it turns out for the B's, you need something else to tag on. So you can't use gluon fusion to look for B's, but you use associated production. And the new physics that we put in doesn't change the associated production cross-section, but it does change the Higgs to B branching ratio. So the signal strength in this model is going to be modified by a kappa B squared in the denominator. In this model, we've got colored particles, so we're also going to be changing the Higgs to glue effective coupling. And so, yeah, the Higgs branching ratio to B's is already 60%, and then Higgs to glue is 10%. So these two processes make up 70% of the width. So if you're modifying these, then you can get a significant modification in the width. And this is kind of exactly what you see in the plot, that as you go to lighter masses, larger trilinear coupling, we have this effect where you have the constraint comes in and then disappears again and then comes back in. And what's happening here is there's an interplay between the kappa b and the width. That means you have a region that you can't exclude purely through the Higgs to BB signal strength. But we see that unfortunately the experimental, this is the current LHC limit, and it's not strong enough to exclude any of the theoretically allowed parameter space. When you do the same for taus, Higgs to tau, you don't need anything else to tag on, so you can look, you can use gluon fusion, which has the larger production cross section. So here we modify the gluon fusion. We have a kappa G, and we modify the Higgs to tau branching ratio, and we modify the width. This still contains the Higgs to B deviation and the Higgs to glue deviation. And we see that now this constraint is a bit stronger, and it's really starting to cut into our parameter space. And for low masses, some of the region where you've got order 1 Yakawas, or Yakawas equal to 1. There's also the Higgs to gamma constraint. Again, this is gluon fusion, and we see that this is even stronger again. The next constraint that we put on is from the electroweak STU observables. And we see in this case, this is actually a little bit weaker and doesn't constrain any new parameter space compared to the Higgs observables. Right, and so on this model, these are all of the relevant constraints. It turns out the z-to-fermion couplings doesn't constrain it. The constraint's too weak, and the same for the g-2. They're just not well measured for the tau at all. So with the current situation is that, yeah, with new physics masses around a TeV, you can have order 1 Yakawas explaining the B mass. So these radiative models are currently not ruled out by the recent Higgs measurements. I said here that I picked the maximal mixing scenario just to show you that that's not a particularly special case. Here we go away from that by a sort of arbitrary amount. And we see that the lines have shifted around a little bit, but the general message is still the same. So this is the current constraints. What about looking to the future? So here we've got some future electroweak constraints, either from the Fcc program here or ILC and CPPC. And we see now here you do get a Z coupling constraint, which is quite useful at small couplings, low masses, and the S&T constraint sort of pushes into the parameter space. That's the electroweak. What about the Higgs observables? Here we've got in the kappa framework now for kappa B, kappa tau, kappa gluon. It turns out these are the strongest constraints. These are stronger than the electroweak observables we looked at in the previous slide. And so we're sort of getting up to hundreds of GeV for small couplings, and then sort of, yeah, TeV scale for larger couplings. However, we can see it's kind of under the arrows here, unfortunately, but even after a future collider program, there's still going to be viable regions of parameter space with order 1 Yakawas that doesn't seem possible to probe in any of these ways. So this is maybe good if you're in the radiative mass generation business, that it seems like your models won't be excluded anytime soon. To actually go after these models and really pin them down, I think this means that you need to go beyond this set of necessary observables we've looked at here, and really in particular models sort of fix a mass spectrum and so on, and look at other constraints like direct production at colliders or other constraints that may be able to do better in particular models. But like I said, we haven't studied that. Okay, I'm quickly going to go through the same process for class 2. It's all quite similar, so I'll do this very quickly. So just notice now that the difference between class 2 and class 1 is that we've got 2 fermions coupling to the Higgs, and this means we now have 3 Yakawa couplings. So there's no trilinear coupling here. There's 3 Yakawa couplings. Oh yeah, sorry. Again, we're just going to look at muon. well, okay, the model classification is good for any for the tau and the muon, and then in the phenomenology, we're just going to look at the muon. Okay, so here is the model classification written in a slightly more compact way. The only thing I want to draw your attention to really is that the softly broken symmetries are now not SA and S psi, but they're S chi and S psi. So the softly broken symmetries are now broken by two mass parameters, the chi mass and the psi mass, rather than a trilinear and a mass in the previous model, in the class 1 models. Okay, so when we look at the radiative mass generation, again, we have, if we consider this this coupling here, which couples the Higgs to the fermions, on electroweak symmetry breaking, we're again going to get a VEV, we're going to get mixing now between two fermions. And as opposed to the scalar case previously, where we had just one mixing angle, now because there's two vial fermions that are being mixed, we get two mixing angles. That's all I really want to say there. Again, we can calculate the loops for the radiative mass in the effective Yakawa. Here, the mass comes out to be very similar. We have the product of Yakawas like you might expect in the numerator, and then the same loop function here as we had in the class 1. The effective Yakawa is slightly more different. There's a different loop function coming in here, g. But we see in this suggestive way that we've written it again, if either theta L or theta R go to 0, if theta L or theta R go to 0 or to pi by 2, then this second term vanishes and we recover the tree level relation. But in general, the tree level relation is violated. Okay, so the benchmark model we're going to look at is this particular choice of quantum numbers. And okay, the way we plot this looks slightly different just because we no longer have a trilinear coupling on the y-axis, but we have this Yakawa coupling on the y-axis. So we don't have this perturbative unitarity bound from Serres Pheno like we had in class 1, but we just cut it off at root 4 pi. And then we plot as low down in that coupling as we need to reach the limit of the product of y chi and y psi is 4 pi. So one thing to note straight away is that rather than a product of couplings equal to 1, like we had in the B case, we can go down to a product of couplings of 0.1. And this is really just it's a reflection of the fact that the muon is an order of magnitude lighter than the B quark. So the Yakawas can be smaller. So we kind of expect this parameter space to be a bit less constrained than the B parameter space and the muon parameter space. Sorry, tau parameter space. We've also put a solid line here when all the Yakawas are equal. And so this is kind of when the Landau pole, you may expect it to be the furthest away because all of the Yakawas are kind of the smallest they can be. And if you go away from this line, then at least one of the Yakawas has to get bigger. But we see that all of the Yakawas can be kind of equal to about 0.6 simultaneously. Again, going off to the right, we see that there's nothing stopping us just having arbitrarily large masses of the exotics. But again, naturalness comes in to cut off the very heavy regions. So we get these naturalness constraints. If we put on the Higgs and electroweak observables, here we just get these cutting into the top corner here. So part of the reason these are weaker, one is that the muon, I think, isn't as well measured as the B and the tau at the LHC. It's only very recently been measured for the first time to be non-zero. Secondly, the Higgs to glue and the Higgs to photon contributions, they're suppressed in the class 2 models compared to the class 1 models. So you have smaller effects in the production and in the width. And of course, here we're not changing the width of the Higgs very much because we don't have we're not changing the Higgs to B coupling. Right, so that's of the analogous observables we looked at in class 1. This is where they sit in class 2. But the new thing we of course have for the muon is g-2, which is very topical at the moment. And so there's been, just to recap the g-2 situation, there was an old result from Brookhaven, this BNL result, which sat 3 point something sigma away from the standard model prediction here in green. And just in the last month or so, the Fermilab g-2 collaboration have released their experimental measurement, and they find a very similar result to the Brookhaven. And the experimental average now sits at 4.2 sigma away from the standard model. And so it turns out that this radiative mass model can also explain this g-2 anomaly if your masses are sitting somewhere in this golden band. In this slice, we've made some choice of the mass parameters, so it moves around a little bit if you vary these. But as long as these scales are kind of all the same, this always points to around the TeV scale or a bit below to explain the g-2 anomaly. One word of warning, though, about the anomaly is sort of contained in this fairly dense slide that was presented by Aida just before the scientific result from Fermilab. And so what this shows is the experimental Brookhaven result, the previous one in yellow here. And there's a theory initiative who are trying to combine all of the standard model calculations to produce the most trusted standard model value that they can. And this is what the green standard model was on this previous plot. This is this white paper 2020 from the theory initiative. So we see here that it sits a long way from the Brookhaven result, and by extension from the Fermilab result, which isn't plotted on here, but it lines up with the Brookhaven. But something to note is that this the white paper result only really uses these two red points immediately above. And so these points with the gray background, these are almost exclusively data-driven, just except from this purple one that has some lattice input. So all of these results use the same sort of data-driven method to estimate. I should say this is just the hadronic vacuum polarization part of the g-2. But they all agree. And we see that until very recently, the lattice results, the errors have just been too large to really say very much. But in 2020, or too late to be included in the white paper, the BMW collaboration released this result here, which we can see has very small error bars. And it sits sort of maybe annoyingly in the middle between the experimental result and the data-driven theory result. And so there seems to be something to be sorted out here in the theory community. One of the positive aspects of this is there's nothing really stopping the lattice results improving as computational power improves over the next years. So we're expecting other groups to be able to match and improve on, and the BMW group themselves to improve on this lattice result. So the situation should become clearer. But we should definitely be ready for the anomaly to go away and it to be some misunderstanding between in the data-driven result, standard model prediction. So in that case, we went ahead and we predicted, so we can see in the gray here, the ultimate Fermilab precision that they expect to reach. So if they reach that and the standard model expectation agrees with it, then we can plot a constraint on our model about what we expect to be able to rule out by that g-2 measurement. And we can see that it's this dashed golden line here at around 2 TeV. And maybe the interesting thing here is that even though we kind of entered into this project thinking about the Higgs observables, even in the most optimistic future scenario, they just reach down to here, this dashed green line. And the Electro weak isn't much better. And this g-2 is really going to give the best constraint on this model in the years to come. Either that, or we're starting to, another way of viewing it perhaps is if you were to see, if this model was a true model of nature, you may expect to first see its deviations in g-2 rather than in Higgs observables. So maybe an optimistic view is maybe the g-2 anomaly is a first hint of a radiative mass of the muon. Okay, so in the last few minutes, I just wanted to briefly mention that in our philosophy, we looked at the deviations from the standard model that necessarily follow from the radiative mass. But of course, in any particular model, you're going to get many other deviations that we haven't looked at. So one that I think I touched on is that these exotics may have gauge couplings, particularly if they're SU3 colored. They can have large production rates at colliders, proton colliders. So you get limits from direct production of these particles. Now, we haven't put any of those on our plots, partly because it's so dependent on the mass spectra and on exactly how they decay, what they decay to, what those couplings are, what the branching ratios are. That really requires a sort of more detailed study of a particular model rather than this more general story we were trying to tell. But going forward, I mean, if you're interested in particular models, that's definitely something that should be considered. We've talked about this, the U1X symmetry, which the exotics satisfy. Now, if that's unbroken, then of course that's a stabilizing symmetry, and the lysis exotic will be a thermal relic. So it could either be dark matter, or if it's colored or charged, you get very strong bounds. But there can be a very interesting dark matter connection here to all of the benchmark models that we discuss in the paper. There's a particle that could potentially be dark matter. And so, yeah, there's an interesting connection to explore there. For particular gauge quantum numbers, it can just accidentally happen that you can write down extra exotic standard model couplings that are allowed by all the gauge symmetries. And in fact, in all of the minimal models we look at, you can write these down. So they do a few things. They typically first break this U1X, which then means you don't have the dark matter connection anymore, but you do have a bunch of collider signatures that you can then go and look for, which yeah, because these particles are then they may decay inside your detector. And another interesting thing we noted just in this minimal B plus tau combined model. So if you're doing both the B and the tau at the same time, and you break the U1 stabilizing symmetry with some of these exotic standard model couplings, then this leads to proton decay. And so we made some estimates, and it seems to satisfy the bounds. But if you're particularly interested in this model, then yeah, it's interesting to look at the proton decay side of things there. So just to conclude, you've seen that we completed a model classification of one loop radiative masses of the charged fermions, or of the B, tau, and muon. We calculated a wide range of the constraints that necessarily follow from this one loop mass generation. And we've seen that these models are currently being probed by the LHC, and tantalizingly, they may even explain the anomaly seen in muon g-2. However, even future experiments seem unlikely to exclude these models, at least on the basis of the observables we've studied, and you may need to go further looking at extra observables that come from these extra couplings or so on that we've discussed to make more headway in excluding particular models. And yeah, finally, I just made some, noted that there's some interesting links to dark matter, extra collider signatures, and to proton decay. Okay, thank you. I think you can actually clap if you, not if you don't.
Thank you very much, Mike, for that really interesting talk. Do we have some questions? I'm aware we're over the hour, so people can filter out if they want, but please go ahead and unmute yourself and ask a question.
I have one question, if I may. You limited yourself to basically just fundamental representations. Did you think at all about higher representations? I'm just thinking about SU3 in particular, whether there are already strong constraints from whatever Higgs to Glu-Glu, because the contributions to Higgs to Glu-Glu might be too large, such that you can immediately exclude possibilities with large SU3 representations.
Yeah, the problem is let me go back to this, for instance. So because it's the same loop that's coming in the radiative mass generation as in the effective Higgs coupling, we see that we've got this both the N2 and the N3 here, which are really counting the number of particles that are going in the loop, counting the size of the representation. But then because we're insisting that we want to reproduce the physical mass, they're kind of just absorbed into the Yakawas. And then when you write the effective Yakawa in terms of the physical mass, those group theory factors disappear because it's exactly the same group theory factors which come into these two loops. So you don't actually benefit in the Higgs observables by going to large representations. You do for the, say, the Electro weak. There you get different dependencies on the group theory factors. But in the sort of the first Higgs observables that you think of, that dependence cancels out.
But how about if you look at a Higgs to gluon coupling? So where you basically have your colored particle in the loop, in the gluons, that may increase.
Yeah, that's true. That will increase. Yes.
Yeah.
We didn't go beyond fundamental.
Yeah. No, I was just curious, kind of, whether one can make a statement there.
Yeah, no, I think that's interesting. It's something that we didn't look at. We just noted this behavior about the Higgs to fermion effective coupling. But no, I think you're right that the Higgs to gauge boson couplings will be enhanced.
Yeah, thanks.
Thanks.
Anyone else? Please go ahead.
So, may I ask the question? Yeah, Michael, thanks for the nice talk. I could not capture from the slides, but I was just thinking about this colored scalars which you had in one of the class 1 model or with P plus tau. Yes, so I see. So then now I see the hypercharges. So you are not allowed to write the trilinear couplings or things like that to destabilize the vacuum. You know, the polar breaking and things like that are not allowed.
Yeah, I mean that's another thing we didn't look at vacuum stability, and I mean you'd get extra phi squared h squared terms or eta squared h squared phi squared eta squared terms in the scalar potential. Again, because those couplings, you can definitely write them down, they're allowed, but the coupling constants are not directly related to the mass generation mechanism. It's sort of like an unconstrained free parameter. So I think if you're focusing on a particular model, it's definitely something you would want to consider. But kind of from our point of view, when we were trying to make these more sort of general kind of model independent type statements about any one loop radiative mass generation models, we chose not to focus on those issues.
Okay. No,
but definitely, if you were doing a more in-depth study of any one of these particular models, you definitely want to think about vacuum stability from basically from the quartics that you get from these scalars.
Great. So if there's no more questions, I think I will stop the recording there.